Linux system programming or system programming in general. We use Linux as a platform here. The objective is not to make you Linux specific. The objective is more about exposing all the issues involved in system programming, especially with regards to driver development, with regards to kernel programming, and how these user space applications which are bound to APIs work. So, we highlight all the general issues. My objective is to touch on the general issues so that when you move from one kernel to other kernel, you should be able to move quickly without much of effort. That's the whole objective actually. But we use Linux as a platform to demonstrate all these services, the drivers, and what all examples that I'm going to demonstrate. I'll be using Linux as a platform. So straight away this will give you mastery on Linux. That's one. Second, it will also help you to understand how generally operating systems work, and then you can move between one operating system and the other applying these skills. So it's not about a specific RTOS, or it's not about a specific GPOS, or it's not about a specific embedded OS. It's about operating systems in general, and then giving you details about how these operating systems change, how the design changes between different platforms, and how you can actually bring down your learning curve, and so that you can move from one OS to other. That's the actual objective. With regards to content of this course, the contents are basically 3 modules are involved in this. Earlier we had a full version course with 4 modules, but now we have taken out networking and there's a first batch without networking module. We have 3 modules now. The first module is about Linux system programming basics, where we touch on the APIs of POSIX, inter-process communication, all this stuff. And then second module we go into kernel programming, and then driver development, and then real time, and embedded Linux. So I'll first give you a little overview of each of these 4, and then if you have any questions on these 4, you can raise the questions and clarify those. So let's begin with the first one. How many of you are familiar with some kind of OS programming? Some kind of OS programming. It could be Linux or Windows or whatever. I just want to know the count of people because this will help me decide the pace at which I can deliver this. How many of you are completely new to Unix world? Completely new. Okay. So I assume rest of you are already familiar, right? So it starts this way. The modules are these. Detailed brochures you can acquire those. But basically overview I'll give you. The first one is Linux system programming essentials. This is module 1. Here we look into basically tools, development tools, various developer tools like compilers, debuggers, and then maybe details about profiling tools, optimization tools and all that. Profiling, build tools. Most of the people who have done some kind of application programming, you could be familiar with these. Right. It's about how to use various kinds of tools on Linux platform, open source tools. We'll be using GNU Toolkit, the GNU compiler collection. We'll be using GNU compiler, GNU debugger, and then profilers, and then some build tools like Automate and so on. So first we look at how to use those tools, how to apply those tools to build applications on Linux platform. That's one. The second part of this essentials will deal with system calls and APIs. Using Unix system calls. Unix system calls fall into various standards. There's something called POSIX standard, there's a BSD standard, there's a system size standard, and so on. So we'll touch on those standards called POSIX, BSD, system size. We'll look at the concepts of APIs, we'll look at the concepts of syscalls, and then how to write applications using these syscalls and using these APIs. So as part of this discussion, what will happen? There are 2 things in this discussion. One, this particular part will make you familiar with application development using APIs. This is the one. And this will also give you a little overview of how internally the memory management or process management or a particular kernel service works. Because when you call an API function or a system call routine, internally it's calling a kernel service. And what we'll do is we'll not just work at the syntax layer, we'll also go into details of how these APIs internally work, what kind of services they invoke, and so on. So this will be a kind of theoretical overview of how operating systems work, how they provide services. That's what will be in this particular part, right? So this is one. And second, OS internals. Now what kind of APIs we look at? I just briefly mentioned few. We'll be using APIs of inter-process communication, I/O APIs, asynchronous and synchronous I/Os, various kinds of I/Os are there these days. We'll look at all types of I/O models, and then we'll look at something called signals or communication APIs, to processors and all. We'll look at multi-threading applications. These days there's a lot of development going on multi-core. So as part of this we'll also touch how to write applications for multi-core. How do you take a single core program and then port it to work on multi-core? Linux is multi-core ready. It has been so for the last 10 years, I think. It's 2.0 kernel now, it's been ready for multi-core and SMP. So we'll be looking into issues of how to actually take a program and write a program to be more effective when it runs on multi-core architectures. So multi-threading will have two discussions again. One, how do you write multi-thread applications so that multiple jobs can be executed parallelly? And second, how do you write multi-threading applications for efficiency and optimization of CPU? How do you use CPUs effectively? How do you write applications to scale performance as the number of cores go up? Right. So like that we'll be looking into, these are the core APIs. Apart from this, we'll touch on small APIs like memory allocation calls and so on. But these are the core areas of APIs that we touch. Inter-process communication, multi-threading, then we have signals, I/O, and so on. After these are done, so this part of it, system calls and APIs, we'll deal with that in two aspects. We'll be learning the OS internals theoretically, also looking at how these APIs work and how to design applications with these APIs. That will finish this first module. The first module is basically essentials. Once you're through with the essentials, you will be ready to understand how kernel internally works and how to write code that runs in k-space, how to write code that can be debugged from k-space, right? So the second module will now be kernel programming and device drivers. So first module, basically issues are those. Module 2, Linux kernel programming and device drivers. Lots of changes have taken place recently in the latest versions of Linux kernel and operating systems at large. Lots of design changes are happening in the operating systems. They are no more like Unix. Lots of changes are happening. So we'll be looking at all these changes happening. Recently microkernels are evolving and microkernels are performing much better than a monolithic kernel. So we'll be looking into all these aspects one after the other. Second module is kernel programming. Now, kernel programming means, first step, understanding the difference between writing an application and writing a piece of code that runs in the kernel space. Kernels actually reside in separate memory zone. Those of you who are familiar would know this. The separate memory zone called kernel space. So how do you write code that runs in kernel space? The primary difference is an application interacts with the user. You can actually use your std out, std in, you can take data, you can show responses. Any piece of code that resides in kernel will not be interactive. It cannot interact with the user directly because kernel space code is for the services for the applications. So writing kernel space code requires you to know about debugging techniques because the applications are not interacting or the services are not interacting. So little of tricks of involved, like design issues and all that. So first we'll look at k-space coding techniques. This is C syntax applied to write kernel space code. Those of you who are not aware of kernel space term or kernel as a whole, at this point of time, don't worry about it. I'll give you introduction in this session itself of what kernel means. Those of you who are aware of kernel could pick up this. The second thing, Linux has got one syntactical approach of doing this job. Syntactical approach to write kernel services. That's called module programming. We'll look at how to write those modules, how Linux actually provides services or interfaces to do this job. Not only Linux, BSD Unix also is providing a similar kind of interface today. Many kernels which are written for mobiles and all that, most of them offer this kind of interfaces. We'll study about these interfaces. Practically we'll explore Linux interface called modules. And then we'll be looking into kernel services. How do we implement? When I say kernel services, these are of three types. They can be file systems, they can be device drivers, or they can be protocols, networking protocols. All these we call as kernel services. Much more, there are also other modules, but these are the core kernel services. Using module programming, what we can do is we can modify a kernel service, we can tune a kernel service, or we can introduce a new kernel service. So we'll explore how to do this. Once we are done with this, we'll be focusing only on this part of it. So this is a kind of Linux device drivers module, is a kind of extension to this. What all we learn here, we split that and apply only on device driver development, because device drivers are the services which are frequently added. Frequently added services are drivers on the embedded domain, drivers for the real-time systems, and drivers for various kinds of GPOS devices. So we'll have next part of it is Linux device drivers. Here we'll be looking into different kinds of drivers. There are different kinds of drivers in Linux. In Linux actually we have something called high-level drivers and low-level drivers. Not just Linux, any operating system has this. We have low-level drivers and then high-level drivers. We'll be looking into both of these, one after the other. In case of high-level drivers, if you pick a book like Linux device drivers, or if you look into web for details of implementation of Linux drivers, most of them deal with this. Most of them are dealing with high-level driver implementations. What I'm referring to as low-level drivers are actually referred to as BSP drivers by the embedded community, and they're also called as the controller drivers for the normal kernel community. So this part of it is for the board support part. This is called peripheral device. So in this category called high-level drivers, there are three different ways of writing a high-level driver in Linux. That's called a character driver, a block driver, and a network driver. These are simply three different approaches of writing your code. So we'll be looking at how these three approaches differ. We'll be writing examples on each of the approach, and then we'll be going into low-level drivers where we explore about the PCI kind of buses, USB kind of buses, all the regular buses which are being used these days, how the driver stacks of those buses are designed, how the low-level drivers, high-level drivers interact, all those issues. So this is the core, this is where we spend most of our time, but to go here we need to learn these things, and also the orientation part. Because when you make a call to a read or a write on a device, internally the driver is getting called, which means you must know the API first to implement this, because through API applications are invoking this. Okay, that's the reason I'm spending little time in the initial part called orientation or essentials. So this is about the driver module. Details about how and what kind of issues we take care here in the browser details are there. Like different kinds of issues are there, like configuration options, how to deal with them, communication between driver and the application. If you have bulk of data, how do you do it? How do you achieve performance if driver is running parallelly? How do you ensure the data, the safety of the shared data when driver is executing parallelly? All those issues are there. When you start writing this, you have to take care of all those issues. So as the classes go on, each session will demonstrate one driver with one issue, and like that will go on with all the classes here. And once we are done with the high level, we'll know all the issues required, and then we'll move on to low level, explore the bus specific hardware access part of it. Okay, so that's about the device driver module. The last module is Linux Embedded and Real Time. It's called Embedded Linux and Real Time Linux. basically the C means solve an issue involved in porting Linux onto any hardware. It could be ARM based or a PowerPC based or a Lisp based. What are the basic high-level issues that you need to look at when you're required to take Linux and then port it onto a board and then build that particular Linux system on a board, make it work there, write applications on top of it, test your applications, debug. So this is the basic theme actually. So this requires us to go into cross-compilers, this requires us to go into kernel builds, this requires us to go into porting kernel physically from host to target, and then debugging there, and then writing applications, deploying them there, and so on. For demonstrations, we'll be using two of the targets. You also can acquire these boards on your own if you want for personal use. We'll be using BeagleBoard. That's one of the boards that we'll be using. It's based on a new architecture, OMAP, and then we have ARM9 targets. So we'll be using ARM9 and BeagleBoard for demonstrating this. But again, the stress is more on generic issues that you need to be aware of before you start porting onto any architecture. So that's where the stress is more. Demonstrations will be on these two boards. Right? You can acquire a BeagleBoard from the vendors. The vendors are in India. It's quite cheaper. So if you're interested, you can acquire BeagleBoard and you can work on the practicals. But we do provide these targets in the labs. So this is about the embedded part. Real-time Linux is about how do you make Linux real-time ready? How do you make Linux an RTOS? Because Linux by default isn't an RTOS. So we look into all those issues involved in making Linux an RTOS platform and how to write applications which are real-time on Linux. Linux already is soft real-time by default because open source patches exist. If the moment you add the patch, then the kernel turns into a soft real-time system, soft real-time kernel. But there are other patches involved to make it hard real-time. So we're looking at both things, soft real-time Linux and then hard real-time Linux. That's about real-time Linux. So these are the four modules. If you have any specific question or if you want any clarification on any of the issues, or if you have a specific issue that is not mentioned here, you can ask questions. This is the overview kind of thing. It's not a detailed content. Detailed content will be in the brochure. You can pick it. Okay. So we'll start with the first session today, the essentials part of it. Today we'll look into the basics of operating system because more or less our whole course is around operating systems. So we'll look into the basics of what an operating system means and what it contains and what exactly the term kernel means. Okay. You can take your logs depending on your backgrounds. Whichever point is new for you, you can log down that. Dictations kind of things and notes will be there for downloads. Lots of times we'll be giving dictations on the fly. These dictations will be there from third session onwards. Okay. I'll run through a simple presentation. The whole idea is understanding an operating system, what exactly an OS means. Different definitions exist, but we'll look at it in a different perspective. We'll look at the operating systems from perspective of a developer, of a programmer. If you look at operating system from a user perspective, you could define it as a platform on which the applications run, or it's an interface through which the user can interact with the machine and so on. From developer's point of view, from programming point of view, an operating system is simply integration of two pieces of code. One is called the user interaction piece. The other one is called hardware processing or hardware management and request processing module. That we call as kernel and shell. So any OS, it could be Windows or Linux or Unix or whatever. Any operating system is simply integration of shell and kernel. These are two different pieces of code which are integrated to create an OS. We have shell, simply integration of these two. Shells, most of you have used Windows, all of us have used PCs already. So the interaction layer, the skin of the operating system is what we call a shell. So shell is responsible for all the user interaction to provide some kind of interface through which the user can pass requests. In the old days we had the CLI mode, the old Unix machines and DOS machines. Today we have the graphical shells. So shell is basically for providing user interaction. And the kernel's job is to take the user request what kind of request a user makes. Normally as a Windows user, what kind of request do we make? We'll be launching applications. The point that we need to understand, those of you who are new to operating systems, users are not interested in the operating system. Users are always interested only in the applications. So user is always requesting some application to be started. Right? So the job of the kernel is to take that request, process that request, and make sure the application launches. The application is given proper resources. And then when application is executing, the application may need access to hardware. The application may need access to CPU time. Providing all that in the background is job of the kernel. So kernel is more or less hidden, abstracted from the user. The user never gets to see the kernel module at all. But the kernel is the core of the operating system. The performance of the operating system directly depends on the performance of the kernel. Okay? So shell is about user interaction. Kernel is about the core services. The core services include hardware management, user request processing, application services. All these are core services. On taking care of these core services is job of that particular module called kernel. So what you're seeing here, in our course most of the time we spend on kernel. We spend very little time on shell and shell scripting. Shell scripting is a technique of customizing your shell. Shell scripting is nowhere related to kernel programming or OS programming. Shell scripting is simply extending the services of shell module, customizing your shell so that you can automate your jobs. That's what is shell scripting. So we'll not spend much time on those scripts and all that. What you're seeing here, this is called generic kernel. A kernel of any operating system would look similar to this. So we'll try to understand the kernel today. We'll try to understand this in different dimensions. First we'll try to understand what components are there, and then how these kernels are implemented and how they are used in various platforms. That's what we'll do now. So this is about generic kernel. If you want to take down, you can take down. I'll give you 2 minutes time. Those of you for whom this is new, I recommend you to take down. If you have read some books or literature, or if you came across some operating system literatures of Windows or Unix, you might have found OS diagrams, which are not same as this is. They're a little different. Unix operating system architecture kind of manuals give you Unix diagrams, and then the Windows operating system manuals give you Windows diagrams, VxWorks, probably VxWorks diagrams, and so on. What we're going to do now, we're trying to understand this in general way so that we can apply this understanding to any diagram and then understand how that is implemented. So what it is. These three that you're seeing here, these three modules that you're seeing here, these are called the core of a kernel. Kernel is a core or the core module of the operating system. It is carrying out most of the functionalities of the OS except one, which is the interaction. Now within the kernel, these three are the core aspects. The first one is architecture specific. This is referred to by Windows as a hardware abstraction layer, a term for this. Unix people also call it as hardware abstraction architecture specific layer. This code actually deals with two issues. One, processor initialization. Initializing your host architecture, because the hardware is designed using some instruction set architecture. It could be an Intel one or a TAPC one or an ARM one, whatever. The processor has got a specific instruction set, a specific way of executing instructions. So this particular piece of code is responsible to initialize the processor and put the processor in a respective mode so that the user applications can use CPU. In case of Intel, we want the processors to be in protected mode by the time the applications launch. But like this, we have different modes in different processors. So taking care of all the CPU initialization, addressing initialization is job of this piece of code. This is called CPU support package or CSP by the embedded developers. That piece of code. The other piece of code in this is initializing all the onboard controllers which are attached to the processor through some buttons. We have a disk controller, we have memory controller, we have network controller, a VGA controller. Like this, we have n number of device controllers which are attached onto your motherboard, isn't it? Processor directly speaks to them through buses. There could be a formal bus like PCI or USB, or there could be a glue logic through which they are attached and the port mapping is done. Right? So either way, we need some piece of code to talk to those controllers and initialize them, bring up them. The job of DSP is that. So DSP and CSP together is what we refer to as architecture specific. If I take Windows, put that onto Intel, then this piece of Windows code will be Intel specific. If I take away Intel and push AMD, this piece of code of Windows is specific to AMD. AMD and Intel are similar, they implement a similar kind of standards, but slight variation is there with respect to AMD because some extensions exist there. Right? Like this, ARM, if you place ARM here, this piece of code needs to be ported, rewritten all over to suit ARM. Rest of the code more or less is architecture independent. Rest of the code has few architecture dependent issues, but 90% of this code is always architecture independent. Which means if you have to port a kernel from one architecture to other, you need to completely rewrite this part of it. Okay, this is where you work most of the time. So this is about architecture specific. Then we have one more layer called kernel. What we are seeing right now is a kernel diagram, a simple view of kernel. This is referred to in the traditional text as in-kernel, because it's part of kernel. It's a core module that's within kernel. We refer to it as in-kernel. Right? This particular in-kernel is responsible to initialize all the required data structures which the kernel needs to maintain to track down the resources. Now, memory is a resource. This piece of code will initialize your memory. Once memory is initialized, memory allocations have to take place. Application 1 requires some piece of memory, application 2 some other piece of memory. You must track down, the operating system or kernel must have some way to track down which memory piece has been given to which application. Which means it needs some data structures in which it can place all these resource entries. So initializing data structures, doing the initial boot up is job of this particular layer called in-kernel. So a combination of these two is what we call as a boot image. So boot image includes the architecture code which will do the hardware initialization when the system starts, and then the in-kernel follows up with initialization of data structures. Okay? Interrupt descriptor tables, memory tables called page tables, segment tables, and then processes. When applications start, for every application there's something called TCD. All this data structure initialization is done by in-kernel. Apart from calling this code to start the boot up. These two together form the initial boot process. Okay? Once system is ready for the boot or ready for the user to use, there's one more component which should be started called loader. Loader is a component which will take a request from the user to launch an application. Whenever as a user you are clicking on an icon in the Windows, or you go into programs menu and click on a program name, you're actually requesting the program to launch. That request is taken by loader, and loader will load the executable image or that particular process image into memory, and then register that to the process manager, allocate CPU, and then make sure it runs. So loader is responsible, it's called system loader. So this is responsible for application loading, or the process loading. This comes up only after boot. Once the boot process is done, the last step of the boot process is to initialize the interface, the user interface, and then to start loader. In Unix terminology, we call this as process 1. Because in Unix, we use a term called process to refer to an application that is loaded right now. So, this is referred to as a process 1, 1 being the ID of it. It's always a fixed ID. We refer to image of these two, a collection of these two, a combination of these two. That image we refer to as process 0. Process 0 is the core kernel, process 1 is the loader. Okay? So, in conclusion, what you need to pick here is this. Any kernel has three important modules, three important components. architecture specific to take care of hardware and to take care of all the onboard controllers. In kernel to initialize all data structures required for the functioning of the kernel, and then loader to receive a request from the user to launch a program. Okay. So these three we call as core. Okay. Now very simple, very simple. Rest of them, there can be any number of this stuff. You are seeing 4 or 5 here. There could be more than this in some other OS diagram. There could be 10 or 20 in some other operating system diagram. These are simply referred to as services. Services are used by the applications when they are executing. Loader's job is to load an application, right? Once the application gets loaded, the application may require network access. It will request the service for network access. Application may require more memory. You make a call to malloc in C, isn't it? So then memory manager comes into picture. Like this, running applications may need some services. And providing those services is job of the service components. So simply put, a kernel is nothing but any kernel. Kernel is nothing but integration of core. I am referring to this as core. Three things are there in core: loader, in-kernel, and architecture specific. It's an integration of core and n number of services. How many services would be there? It depends on what kind of OS it is. But simply, any operating system's kernel is core plus services. Core is always specific to hardware. It is targeted on a specific hardware architecture. Windows, the core is for PC platform. PC platform, we have Intel architecture, AMD, and so on. Embedded, we have ARM RISC processors. So with different types of them are there, MIPS and so on. So core is implemented targeting an architecture. Services are implemented depending on the type of kernel it is. Play with this part first. Any questions till this part? If you want, you can take 2 minutes time. If you have any questions, you can pass it on. DSP is a piece of code that's responsible to initialize the onboard controllers so that the processor can now perform handshake and interact with them. You have a hard disk. Simple way to understand this. If you take a hard disk, we don't connect hard disk directly to processor. We connect hard disk to a hard disk controller on the board. And through the controller, CPU talks to hard disk. So if you're writing hard disk driver, obviously a driver is running on CPU, isn't it? So driver cannot directly access hard disk. You need to go through controller. Right? So you need to have the controller enabled for hard disk to be detected. Doing that job is job of this. I've just given you one example: timers, interrupt controllers, lots of other chipsets. Initializing that is job of DSP. System calls are simply interfaces through which the applications now can invoke these services. So it's simply an interface. It could be a function in OSs like Unix, or it could be a method in the operating systems like Windows, which are object-oriented based. So depending on that, they are simply interfaces through which application can call any of these services. As I mentioned earlier, user is interested in the applications. Applications are interested in the services. Applications are not interested in core. So core is the key. If someone claims that I wrote an OS, what he needs to write actually is core. Once you are done with the core, rest of all services you can manage. You can put these services depending on the need. Okay. So the number of services could be less or more. It all depends on the kind of platform we are targeting this kernel for. Let's take one more small view of this. Let's make an assumption we are writing our own kernel. If we are to write core, what we need to know first, what we need to first decide. Let's make an assumption we are writing our own kernel, which means we need to write core, we need to write services, integrate that, create a build image and deliver it, isn't it? So if I'm writing core, what do I need to know first? What should I decide? Architecture. Is it going to be for ARM or TPC or RISC or CISC and so on? So once I know which architecture I'm implementing it for, you need to study that architecture instruction sets. You need to study the architecture in detail. may not be complete in the workings, but basic details, programming manual of the architecture to implement this piece of code. Okay? Once we are done with this, how do we decide how many services we put? Let's take an assumption we are done with the core. We have implemented our core. Now we need to implement services. How many services will be implemented depends on what? Who is using services? Applications. Now applications are using services. Applications are used by users. So now, how many services we implement, that purely depends on what kind of users we are supporting. We are supporting a multimedia user, we are supporting a developer, we are supporting a normal user. If you are supporting a PC user, what kind of services you put, more or less? More. Why? Because PC is a general platform on which diverse applications are used. We have audio, video, different kinds of applications, gaming applications, text editors, isn't it? Different applications have different needs. Some applications need memory, some need network connectivity, some need device access, hardware peripheral access, some need the access to processor time, more of processor time. Like this, you have different kinds of applications with different needs. So we'll have to now look at all the applications possible for that platform, like a PC platform, and then come up with a design of list of services. So how many services would be there? It is purely dependent on which platform we are targeting this kernel for. There are three platforms: desktop, server, embedded, real-time. Okay? Now, very simple. Apply this formula. Core plus services is the kernel anywhere, wherever you go. Difference is, first, let's pick up PC. How many services will we have on a PC? Less or more? More. Obviously more. So PC kernel is heavy. It has lots of services and core targeted towards desktop or server architectures like Spark or architectures like Intel AMD. Right? If you take embedded OS, what will be the embedded OS of that? Configuration of such a kernel. How many services will we have in the embedded OS? Less. Specific services for the specific applications. So we have core targeted towards the embedded architecture, and services will be less in number, targeted towards those specific applications which are used on that device. Which means embedded project 1, the configuration is different. Embedded project 2, the configuration could be different. The services you choose to put in OS 1, the same services may not be repeated in OS 2. Clear with this? Clear now? Like this, each area, depending on the type, depending on where you are deploying, the packaging changes. The problem is most of the people who are getting into OS learning, they're not looking at this side. They're viewing Windows as different, Unix as different, VxWorks as different. There's no unification view. If there is no unified view, you get confused. Whenever a new OS comes up, you'll again learn at the system call level. Okay? So let's go into a little of writing. I want you to, those of you who are new to operating systems, what you need to put down is, you need to put down this thing called core plus services is what makes up a kernel. That's the first point. Make your own point. The first point is the core components, which include the architecture dependent, which include in kernel and loader. These make up a kernel core. And then rest of the components are service components. Make your own sentence. Next one, GPOS. Just put the side heading GPOS. The desktop and server operating systems are referred to as GPOSs, general purpose OSs. These general purpose OSs will have too many services. And that's the reason why they are very heavy. The Windows Vista, Windows 7, all these are examples of it. So first write down GPOS and then write down these GPOS kernels carry core targeted GPOS kernels carry code targeted for PC and server architectures. Intel AMD Spark, Intel x86-64, and so on. They carry code targeted for PC and server architectures, or desktop and server architectures. In case of PC, you can write desktop. They carry code targeted for desktop and server architectures. And services for diverse applications possible on desktop and servers. Possible on desktops and servers. So that's the reason a PC operating system is quite complicated. Lots of services and lots of new drivers, lots of new applications keep coming. You need to modify kernel to support them. It becomes very heavy. The second type, embedded OS. The second type is second area where we use operating systems, embedded OS. So I think now you can frame your own sentences. Code targeted where? Towards what? While writing core module for embedded OS, what kind of architectures do we target? Usually RISC, or the embedded processor architectures. Right? So, these kernels carry core targeted. These kernels carry core targeted. These kernels carry core targeted or targeting embedded processor architectures. Embedded processor architectures. How many services? Less, isn't it? Not just less, but specific. You need to know what application you're running on that embedded device before you can add services to it, isn't it? So core is one, and then services, limited services. Limited services specifically designed for applications on that device. Specifically designed for applications on that device. Are you clear with this point? Each project, you may have the same core, or you may have a different implementation of core targeting different architectures. Not just the core is changing, you may also see a change in services. One service may not be required in one implementation, it will be required in the other. For instance, networking may not be required in few embedded devices. In few embedded devices, you may need an OS with networking support. Like this, the services change. Now, the last one, the real-time OSS. That's one more way an operating system is used is RTOS, isn't it? The best way to understand RT is to separate it from embedded. Embedded and RT are two separate issues actually, but they can coexist. That's a different issue. But if you have to understand real-time issues, you must separate these two and study real-time as a subject and embedded as a different subject. Then you can be very effective using them together. Okay. Now when we talk about real-time, first let's explain the difference. Real-time is also core plus services. Same as what GPOS is, same as what embedded OS is. The major difference is this. When applications make a call to a service in a GPOS or an embedded OS, how much time the service takes to send a response back, the time is usually variable. It's not fixed. In RTOS, what we do, we implement the services in such a way that always, irrespective of the load, the response time is fixed, deterministic, predictable. If the response time of the services is fixed, then applications can be designed to be deterministic. What are real-time applications? They don't execute faster. They're simply applications which are designed for deterministic and predictable behavior, isn't it? Predictable outputs. Whatever the timing is. In few applications timing could be more, in few applications timing could be, the resolution could change, isn't it? But basic qualities, predictability and determinism. If an application should execute in deterministic way, the services it is calling, those services should be in deterministic way. If you make a call to malloc and you never know how much time malloc takes to return, then your application cannot be guaranteed to finish off in 5 seconds time, isn't it? The amount of time the application takes depends on what kind of calls you're making in the application, and if those calls are going to OS, how much time the operating system service is taking to respond back, isn't it? So in RTOSs, what they do, they write these services in such a way that services always have fixed time responses. Quality of service is more important than the number of services. So can an RTOS be on a general GPOS? Can you have a GPOS with RTOS quality of service? Yes, telecom domain is a perfect example of it. Lots of routers, they use bulk of operating systems which are bulkier than PC-based operating systems with real-time responses. Right? Like this, we have real-time in desktop and server machines, real-time also in embedded devices. Which means embedded OS can be real-time, or a desktop server OS also can be real-time. Real-time is simply quality of service and how much time the service is being, how much time the kernel is taking to respond back. Is that time fixed or not? That's what we mean when we say real-time. Other factors exist, but the major factor is this. Okay? So, how do we write this now? It will carry core, targeting what? An RTOS core will target what? Desktop, server, embedded. It could be any, depending on what kind of platform it is for. So, RTOSs, these kernels carry core modules. RTOS. These kernels carry core modules targeted. These kernels carry core modules targeting desktop/server/embedded architectures. They can be for RISC or CISC. Desktop/server/embedded architectures. And services which offer fixed time responses. This is the basic view of kernel. So if you look at a Windows diagram now, you should be able to catch why Windows has those services, because those applications need those services. Whenever you look at an OS diagram, you need to interpret that using this. Then it will become very easy to know why these services are needed, why a new service has come up, maybe a new application type is supported. Obviously, new service should be there to support that. Okay, so far? Okay. So GPOSs, embedded OSs, and real-time OSs. Depending on the configuration, they have different names. But basically, they are all core plus services. Now, with regard to Linux, because we'll be using Linux for all the practical purposes here, but throughout the course, my objective will be to deliver this subject at generic level. You can apply it to any OS. That's how we go about. But for demonstration purpose, I'll be using Linux, and most of jobs would be on Linux domain. In some projects or the other, you'll come across Linux. So, Linux first point is this. Linux is not an operating system. That's a major misconception. When we say Linux, we are referring to this implementation in open source. What is this? Only kernel. It's not shell. It's just kernel. To make an OS, what you need? Shell kernel, isn't it? Linux is just kernel. There's no shell to it. Linux is open source code that someone wrote and put that on the web, and that code contains services, that code contains core. You can take it, adapt it to any of those three. You can take it, adapt it to make a GPOS for desktop. You can take it, customize it, and use it on server. You can take it, customize it, use it on embedded device. Take it, customize it, and use it on RTOS. So basically Linux is that. It is simply open source kernel. And this open source kernel has not been built for a specific use. Initially, Linus Torvalds wrote code. He wrote code for Intel architecture for desktop. Later, contributors from various parts of the world, they've added to this project lots of other code. Some people have added code for PowerPC porting, someone for ARM porting, someone for MIPS porting, and so on. So today we have this implemented for more than 8-9 architectures, commercial architectures. And lots of services have been added by different developers across the globe. So now we have a huge source code base, which you can download, customize, use any way you want. So instead of going for your own embedded OS, if you can download the source code, choose what configuration you want, what architecture you want for, then it's more easier. Development time can be reduced, isn't it? And then you can have this complete customized operating system targeting your device. Yeah? So Linux is simply kernel which can be adapted into a GPOS or server OS or embedded OS or RTOS. Now doing this job are the companies called Linux distributors. You might have heard about Red Hat Linux or Novel Linux or whatever. These are simply operating system distributors. They are like Microsoft. Microsoft and the difference is Microsoft is writing its own code and distributing it. These guys are downloading code, packaging it and distributing it. That's the only change. Basically they are OS vendors. Okay. So Red Hat, what it does, it fits the code from Linux kernel website, the open source website, as the shell. It will add its own applications on top. Sometimes the applications are Red Hat proprietary, sometimes open source applications from other sources. It creates a bundle. It creates an OS out of it. Okay, and then distributes it, provides support for it. Now when I'm distributing, obviously I should choose what? Let's make an assumption you're an OS vendor. You're owning a company which distributes an operating system. What you should do first, you must choose the target market, isn't it? The target market, various verticals are there. Embedded vertical, the server vertical, the desktop vertical, isn't it? Multimedia vertical, then real-time vertical. So we download kernel, add the shell, add the applications, and then see which vertical we are giving it first, customize it for performance on that domain. Red Hat Server, RHEL is what is referred to as today. This is for enterprises, for server side. Fedora is for desktop. Ubuntu is for desktop. Likewise, Monta Vista is for embedded. So various distributors are there who are making Linux or who are making operating systems based on Linux. Okay? And distributing it for various users, providing support. Now, for the software developers, two options. If you're involved in embedded project or real-time project, you could take a distribution from a vendor, use it directly, like Monta Vista Linux, RC Linux, and so on. Or you could download and do all the work on your own, customize and port. Okay with this? So Linux is simply open source kernel and not an operating system by itself. If you start on Linux with this particular view, then Linux is very easy to master. The moment you think it's an operating system, you expect it should be this way, it should have this interface. Why Red Hat is giving me this kind of interface and not like the same interface is not in Ubuntu and so on. You become very specific to a product, and then you expect the same features in the other product. Okay. So Linux is simply kernel. Kernel is not visible to user. And user is seeing what? Interfaces. Distributors can design any interface they want. Ubuntu doesn't look like Red Hat. Red Hat doesn't look like Mandrake, and so on. Okay. So Linux is open source kernel and not an operating system. It can be made into an OS depending on which target you are, which target platform you are looking at. You can design an OS out of this for that target platform. And Linux distributors are doing this job. Okay? So we can make that point, those of you who are new to Linux. If you have to work on embedded Linux, there are two ways to work on it. One way, you go and talk to an embedded Linux vendor, a distributor who is distributing Linux for embedded, like Monta Vista, buy his distribution, use it right away. The other way, download kernel, download the open source applications or write your own applications, learn how to customize, build your own Linux. Okay? Building your own Linux is a normal way that we take up in education because that will give you skills. Using off-the-shelf is always easy. That you get a job done in quick time. But because we need to focus on learning more, what I do is I go with the first approach. Download, modify, customize, and have your own Linux instead of using a ready-made off-the-shelf. So in the course, the last module is about that. RT and Embedded Linux is about downloading kernel source, customizing it, putting it on board, booting it up, and so on. The other option is you could be working on Monte Vista, Timesys, some ready-made distribution. In that case, they will give you tools, they will give you procedures. Alright? So this is about introduction. If you have any question, you can take a recap of 2 minutes. Those of you who are new, if you have any question, you can pass it on. We'll look into some more issues and then wind up. There's one more last issue, and then we'll wind up. So far, it's been clear? So various areas we can use this on, desktop servers and so on. Let's look into one more issue. Carefully watch this. This is how our software looks like. This is what the whole software package is, isn't it? We have kernel with some services and core applications. Now, one of the most important functionalities of the operating systems of late, earlier when operating systems were designed, this functionality was not expected. But later, when number of applications grew, when the number of applications used by the user and multi-user systems came up, this requirement came up of protecting one application from accessing its memory space by other application. Similarly, protecting the kernel from direct manipulation by application. Because the stability of your system that's needed. If you allow the kernel to be modified, if you allow the kernel services or kernel data structures to be altered by an application directly, then a malicious application like a virus can deliberately tamper some data structure and destabilize your system. So protection was needed. Protection was needed between applications. One, protection was needed from applications to kernel. So later, initial days, DOS, and those days this was not considered, but later, hardware vendors, the processor vendors, came up with various techniques to support that kind of protection. At the hardware level, we have something called is protected mode, wherein you can actually switch your processor into a mode where it will see memory as segments and not as an array. One way you can use the CPU, if I'm CPU, if memory is connected to this particular processor, it can view memory as starting at 0, ending at 4 GB. Whole is big array of bytes. That's one view. The other view is, I'll partition this logically. I'll see this as block 1, this is block 2. Any code that's in block 1 should not access block 2. That's possible if hardware vendors support it. So we have something called privilege levels. Intel, Pentium, initial versions onwards, this was there. These privilege levels are nothing but a mode in the hardware, in the processor called protected mode. The moment you push this hardware onto protected mode, it will view memory as segments. And you can place applications into individual isolated segments so that they don't access the region of other applications. Similarly, you can put kernel in one segment so that the applications don't access kernel. This is for protection stability. Okay. So now, please carefully understand this one last point. In Intel, I'm just taking an example of Intel. We'll look at this for the RISC architectures when I talk about the embedded. It's not complicated, it's very simple. We'll be going through all this in detail in memory classes. For the time being, because I'm speaking about some other object or some other issue, I'm not going into details of this. But in Intel, there's a mode called protected mode. At the boot time, the core kernel will switch the processor into that mode. Which means by the time its system is ready for the user, CPU is in protected mode. So one small issue. There are 4 privilege levels which Intel refers to as rings. Ring 0, ring 1, ring 2, ring 3 and so on. Any code These 4 privilege levels for the time being you can assume as 4 blocks of memory. You put 1 GB of RAM or 512 MB of RAM, whatever amount of RAM that you have, logically it is shown to processor as if it is 4 blocks, 4 different segments. And this is done by the CSP code, the boot up CSP code. So ring 0, ring 1, ring 2 and ring 3. Ring 0 is called the supervisor mode and ring 0 is the location of the kernel. So kernel is isolated from rest of the applications by placing that in ring 0. Applications always reside in level 3, which we call in software terminology as user space or application space. We call this in software terminology as kernel space. So initially when I was talking about the course content, I was mentioning case-based programming. What I was mentioning is how do you write code in ring 0? Because normally when you write applications, you are loading the applications into ring 3 and executing them. Case space is different because you write code and put that into ring 0, which means lots of issues have to be considered, especially safety issues. Okay, so we have ring 0, 1, 2 and 3. Now, 2 kinds of kernel architectures are there. The reason why I came into this one. 2 types of kernel architectures are there. The first architecture is called monolithic kernel. Okay, basically kernel is 4 plus service. You put that into one image, you load that into memory at the boot time, system will be booted. Now this image when it gets loaded, how it gets loaded, that's what we are saying. You can build the image in such a way that it can be monolithic kernel. Monolithic kernel means basically core plus services together built into one executable. Complete single piece. File systems, drivers, IPC, all the services plus core together into one exe. That's called monolithic. And monolithic kernels, when they are loaded to ring 0. Applications are loaded to ring 3. And monolithic kernels don't use ring 1 and 2. So there is no ring 1 and 2. Even if the hardware provides ring 1 and 2, we disable ring 1 and 2, use ring 3 and ring 0 only. Ring 0 we refer to as kernel space. Ring 3 we refer to as user space. So applications are in user space. These dots here are indication of the partitions that we're creating. This is called the memory partitioning model. Right? I'll be going into details of it. For the time being, there's a point that we need to understand. For the reason I'm showing all this. So this is region 1, domain 1, domain 2, domain 3. Each application is isolated in its own segments. Kernel is abstracted from the application in its own segment. So kernel and applications are loaded like this. Examples of this, all operating systems which you have used so far on the PCs. Windows, except of Windows Vista and Windows 7. All the previous versions of Windows. All Unixes, all Solaris. All desktop and server operating systems we've been using so far, almost all of them are monolithic. Which means kernel resides in ring 0 called kernel space. Applications will be in ring 3 called the user space, and kernel is a single image of services plus core. That's monolithic model of implementation. So if you're writing, the writing is types of kernels. Types of kernels, the first one, monolithic kernels. The reason why I'm spending on these, as we go through the classes, I'll be spending on the fundamentals more, because later concepts are easy once you have this foundation. First one, monolithic kernel. To write down one point, monolithic kernels are statically linked. Monolithic kernel is highlighting, and then write down. These are statically built kernel images. These are statically built kernel images. These are statically built kernel images by integrating core modules and services. By integrating core modules and services. By integrating core modules and services. So one exe, you load it and load it. Windows is example of it, Unix is example of it. Most of Linux distributions are examples of it. Next point, monolithic kernels are loaded to kernel space / supervisor mode. Ring 0 is called supervisor mode. Monolithic kernels are loaded into kernel space / supervisor mode / ring 0. Ring 0 is an Intel specific term, so I'm not stressing much on it. In ARM you have some other term for the same. And applications reside in where? Ring 3 or user space. And applications are loaded to ring 3, privilege level ring 3 / user space. This is about monolithic. There has been a lot of work happening in this area. Recently, lots of changes have taken place. There is one more design, that is this. What these people do, they call it microkernels. So monolithic guys don't make use of 1 and 2. 1 and 2 rings are almost disabled even if they are there. Right? Microkernel people, what they do, they take the core and they put it into ring 0. They take the services, put that into ring 1 or 2, their choice, or both. And they put the applications into ring 3. So this is a 3-layered architecture, or 4 layers sometimes, depending on the number of rings available. So this is called kernel space. Now the kernel space has what? Only cores, not the services. Services are pushed into, this is called the middleware. In terminology, we refer to it as middleware. So that's where the services go. Applications are same, like monolithic in user space. This is monolithic. This is micro, sorry. Okay, down next one, microkernel. Kernel image is built using core components. Kernel image is built using core components. Kernel image is built using core components and deployed into ring 0. Kernel image is built using core components and deployed into ring 0 / supervisor mode or kernel space. Kernel image is statically built using core components and deployed into ring 0 for kernel space or supervisor mode. Services are built, kernel services are built as loadable components. Kernel services are built as loadable components and deployed on demand to ring 1 or 2, ring 1/2, to ring 1/2, middleware space, in the bracket or put a slash, it's up to you, middleware space. And applications as usual, they're always deployed in ring number 3, which is, ring number 3 is user space. Now the initial course contents will make sense to you now. Now you can see some issues with regard to the content. I said we'll be writing drivers. So where we'll be writing code now? If it is monolithic, our driver will be in ring 0. If it is micro, driver will be in ring 1, 2. Linux is not both. Linux can be made anything. So we have to study that module. You have to study this module, which means you will get the skill of working on microkernels and acquire the skill of working on. That is the skill that you need to carry when you say I know operating systems. Not specific Linux driver implementation or specific Unix driver implementation. That will help you instantly to get a job. But the sustain and perform and to bring down your learning curve when you move from one OS to other, these skills you need to equip with. So that's where I focus more on. Instantly, the rest of the issues will help you. Linux specific issues. Now Linux so far is monolithic. So far in all the implementations across embedded, real-time and the desktop server editions, all distributors are making Linux-based operating systems as monolithic. Recently, an attempt to build a microkernel out of Linux, it's not 100% microkernel, but close to it, is Android. Google Android platform is the first Linux microkernel approach, and Intel's Mobilin is one more microkernel approach based on Linux. Like this, we see future now shifting into microkernels because of some benefits here. Most of the RTOSes are already microkernels, QNX, L4. Like this, most of the RTOSes are already microkernels, which have the highest clearance of security. Most of them are, Integrity is one female product. This is the highest secure operating system. It cleared all the EL security levels. So like this, most of them are microkernels. So there is a need or there is an activity going on right now in most of the RTOS vendors. They're trying to take Linux and they're trying to make it microkernel. So when you say I'm a Linux driver developer or a driver developer, you should know the issues involved in writing a driver here and writing a driver here. Both are kernel programming, but the issues are different. Okay? Let's now try and compare these two identified issues. Which is better for performance? Okay, let's put it this way. Do you see any advantage of microkernel architecture over monolithic? Any advantage, one or two? Any benefit? More secure. Can you elaborate a little? More secure from what? Of what? What are we securing there? The core kernel, isn't it? So, with respect to security, microkernels are more secure and more reliable. The reason is this. Is there a possibility of new devices coming up? We have built an OS, we have released it, we have 10 drivers in it. Is there a possibility tomorrow we need to add 10 more drivers? Yes, because devices are always increasing. And is there a possibility that others write drivers for our OS? Third-party vendors. Third-party hardware vendors will write drivers for our OS. Is that a possibility? That should be enabled, isn't it? All the time if the vendor is writing the driver, then it will be vendor-locked product. So we have to allow third-party vendors to write drivers and deploy in our OS. Now how can we trust the third-party code? If I put the third-party code in the kernel space, what is the guarantee that that code is safe and not tamper my existing kernel? Isn't it? That's the problem in monolithic. In monolithic, the problem is adding new services is needed. We need to allow third-party vendors to add it, but we cannot trust a third-party vendor's implementation. Sometimes a wrong implementation, an invalid pointer access may crash the kernel. And that's happening in Windows. You see lots of crashes happening in Windows because lots of drivers are there which you install whenever you plug in a new device, which are vendor specific. A bug in the driver will cause a kernel crash. So monolithics are not stable as they grow, as they extend. The reason is services are in kernel space. So security-wise, monolithics have the problem. The benefit is you are separating the services from the core. As long as the core is secure and safe, you don't have to reboot your system to recover from an error. Okay? Because even if a bug is there in the driver, the bug will be in a specific partition or a specific segment that's in the middleware zone, that's not in the core zone. All your data structures are secure here and no one can access them. And the drivers which the third-party vendors are writing, they are in. So that's how it is more reliable, more secure. You need this kind of security, this kind of reliability guarantee in the avionics industry. Most of the hard real time, this kind of security is needed. and integrity is the first operating system, first access today, which has the highest security clearance because of this model, QNX, this model. Most of the RTOSs commercially today are this model. Okay, so benefit with regard to security, if you compare them in the criteria of security, microkernels are more secure and more reliable when compared to monolithic. Yes, we compare in all the criteria. Yes, performance as you mentioned, which one will give you better performance? Monolithic. It looks like monolithic gives you better performance. Yes, to an extent it's correct, but two issues are here. The reason why we would say monolithic gives a better performance because there's only one level of communication here. Application will cross this barrier through a system call, through an interrupt-based system call, and access a service and service response. In the case of micro, we have two barriers, isn't it? We have the application talking to driver, and maybe the driver needs to access the hardware through this barrier crossing this. The two levels are there. But the difference is, if you compare these boundaries, it looks as if monolithic is more better. But there's one more small issue. A shift from ring 3 to ring 0 is always through an interrupt. Hardware cannot move from that segment to this segment without a context switch. Context switch means drop the current program whichever is running and flush all the registers and reload the registers and load some other program, move into some other mode. That's what is context switch. So from user space to kernel space, from ring 3 to ring 0, always it is through interrupt, through a context switch, a forced context switch. Okay? From ring 3 to ring 2 is possible through IPC. IPC means what? Two applications can communicate without needing an interrupt or a system call, simply by exchanging the interface functions. Function A of application A. Application B can call function A and talk to application A. This is simply called inter-process communication. Okay? You can have communication between ring 3 and ring 2 or ring 1 through IPC. Now let's make an assumption that most of the part of our driver is here. Right? Then communication between the application and driver is being executed using IPCs in place of system calls. That's a huge edge. Because system call, one service. If 10 services are needed, you need to make 10 syscalls. 10 syscalls, 10 transmissions. Isn't it? That's more performance, that's more cost. So in this model, what happens is, you will have a better performance because the communication between the middleware and the applications is through IPC. And that's what we have understood earlier. Applications are interested in services, not in the core. So take out the core. Whichever services are mostly needed, put them here. Just have an interrupt handler here. Rest of the driver code, put it here. Okay? Which means, if I'm writing driver for microkernel, I should make my driver available through IPC to applications. If I'm writing a driver in the monolithic kernel, I should make it available through system calls. Like this, the issues differ of how you write your driver. So clear with this part? Performance-wise, Micro has proved, recently Micro has proved that it is much better in performance. But there are some limitations of Micro also. It's not that monolithic only has limitations. The problem with Micro, can you see any problem with Micro? The problem is there actually. Right? There, the hint is there for the problem to predict. They are not used. Ring 2 and ring 3 or ring 1 and 2 are unused. That's the design of kernel. See, the hardware provides you privilege levels. It is for the software to decide whether to use them or not. It is for the kernel to decide. So most of the monolithic kernel, the monolithic approach itself is an approach where ring 1, 2 are disabled. Because they never felt the need of that when they initially designed the kernels. And the people who were looking at these two rings to be used, they call themselves as microkernel. That's how this term is required. Initial approaches, all the initial approaches, they didn't feel the need of it. Because they never predicted that the OS would grow. not just memory, instructions also are there in it. Privilege level means three things: access to resources like hardware registers, executing privilege instructions of the processor like disabling interrupts and all, and memory. So I'm not going into details because this is not session of that. We are focusing on micro monolith. Here so far, so any problem that you can see with micro? Layers are more, so what's the problem? Layers are more, application and middleware service communication has become more easy. Before I mention the problem, there's one more benefit with micro I mentioned about it. In operating systems like QNX and many RTOSes which implement this, there is one service called reincarnation service. That reincarnation service, what it does, when the service has a problem and the service crashes, it will store the state of it and restart it on the fly. Which means even a service crash will not bring the kernel crash. Not just that, the services can be restarted. Most of the RTOSes have that. So reincarnation services are possible, or fault tolerance is possible. Where? In microkernels, because the drivers are in separate space, you can apply fault tolerance. In our course, we'll see how to apply fault tolerance in monolithic drivers also. That's where the research is happening these days, and I'm going to present you a few implementations of that type. Not yet in the kernel, not yet in the Linux so far. Maybe next two versions it will come up, but we'll have some examples on it. Okay, so far till here? The problem with micro is this. It is very difficult at the implementation time to decide which service will go into which partition. Now, the reason for that is, lots of services have type touching. We know that kernel data structures exist, right? For example here, file system is a service which will organize files on your disk, right? But the file system service doesn't work without a driver for the hard disk. And you need to put them together if you want performance. If I put the driver here, just make an assumption, I put the SATA driver or SATA driver or SCSI driver here, and the file system here, then you need inter-process communication. They cannot share data anymore, isn't it? So I need to put them both there in the same partition so that